Hello everyone. Today I'll deliver a lecture. The lecture topic is bearing capacity of mat or Raft foundation uh, using Meyerhof equation, and the second topic is bearing capacity of mat or Raft foundation using based on SPT or from SPT data, and last one the bearing capacity of compensated foundation. So compensation or compensated foundation is nothing but it is a specialized type of foundation where the weight of soil, this is the foundation, the weight of soil is excavated. So we'll extract the soil and roughly equal to or greater than the weight of structure being constructed. So this soil will be excavated from the equal weight or greater weight which is structure will be constructed, and the technique is reduced pressure exerted of soil below the foundation. Okay, so let's see. Here's the foundation. Here's a common some definition we have seen here. Mat foundation, when more than one line of column is supported by the concrete slab, that it is called mat or of a mat foundation. And the mat foundation are generally used in the soil that is a low bearing capacity. And here is some factor of safety for mat foundation. So for a mat on clay, on the factor of safety should not less than 3 or under dead or maximum livelihood, and another one is under the most of extreme condition, the factor of safety should be at least 1.752 and 2. For the mat construction or constructed over the sand, the factor of safety will be 3, and of 3 should be normally used. So we can see here compensated footing. The footing is this is the normal soil, and the foundation is appeared after the excavation. So after the footing is placed here, we know QL over Q by A. So gamma point sigma point df, it is the removing after of soil. So that's why we'll minus from the Q divided by A. So let's see. So here we can see another another some what I will say some information of about mat. Under the normal condition of square and rectangular footing are economical for supported column and walls. However, under the certain circumstances, it may be desirable construction footing that supported line or two or more column. These footing are referred to as combined footing. When more than one line is column is supported by concrete slab, that is called mat or Raft foundation. Okay, so mat foundation are generally used in soil that has low bearing capacity. Under some conditions, spread footing would have to cover more than one half a building area, and mat foundation might be more than economic. Okay, so here is some several type of foundation are used currently over the world. You can see flat plate and mat is uniform thickness, and flat plate thickness is under the column flat plate with pedestrian and flat basement wall as the part of the mat. So we can see here there's some picture of different type of mat foundation. So you can see here this section as a two-story building, and plan is here. So flat plate is using here. So we can say this is the flat plate. This is the section. We can see a flat plate thickness under the column. So this is the flat plate and thickness under the column. So okay. So we can see here another type of mat foundation is common use flat plate with pedestal and slab with basement wall as a part of mat. So you can see here from this graph. So the ultimate bearing capacity of mat, the gross ultimate bearing capacity of mat foundation determine the same equation we have found from Meyerhof and shallow foundation. So we can see here the Meyerhof equation is taken here, and we can see here the net ultimate bearing capacity will be Q net equal to Q ultimate minus Q. Okay, so we can see again the factor of safety. So there is some factors. We can see a mat for a mat on clay. So this is for clay soil. The factor of safety should not less than 3 and under dead load and maximum load. And however, the most extreme condition, the factor of safety under should be at least 1.752 to 2. And mason construction over the sand, if the mat is constructed in sand like Saudi Arabia and Middle East, then the factor of safety of 3 should normally be used. Okay, so under the most working condition, the factor of safety against bearing capacity failure mat, it is very larger. Okay, so let's see an example. We can see here okay. So here is an example. We can see here that determine the gross ultimate bearing capacity and net allowable bearing capacity of a mat condition with dimension is given 15 meter into 10 meter on the saturated clay. So this clay with C equal to 95 km square and SH to 18 km per cubic meter and depth of footing is 2 meter. Use Meyerhof bearing capacity. Assume the factor of safety is 3. So these data are given. So clay soil B is 10 and C all the data is given. So phi is when phi is 0, then we can use NC and Q and gamma. How will get this? We will find this from Meyerhof bearing factor. So you can see here when the phi is 0, then NC equal to 5.01 and Q equal to 1 and Meyerhof n gamma equal to 0. So we have taken this from Meyerhof chart. So shape factor and shape factor CS, shape factor QS, depth factor CDQ, depth factor QD, and inclined load factor we're taken from equation. Okay, so gamma prime equal to gamma saturated minus unit weight of water and found 8.19 and Q equal to gamma prime into TFN for 16.38, and putting all this value in this what I will say in this equation and found 585.7.3 km meter square. So we know the Q net equal to Q ultimate minus Q and found 569.38 and Q allowable is Q net divided by factor of safety and found 189.79 kN per meter square. So if we see this in here, that the same this math example and this example are same. We can see here all the data is given. C is 95 and saturated 18 and DF equal to so we can see here we will use this equation, and when phi is 0 and we have found from Meyerhof equation C is here and Q equal to we have found here. So this is the shape factor we have calculated 1.13 here. This is 1.13 and found QS equal to 1, CD equal to 1.04. So you can see 1.04 here, and all the data is found and ultimate found here, and the Q net is found 569.38 which is 569 kN square, and allowable net divided by factor of safety which is 189.6. Okay, so okay, so we can so we'll now the topic 6 cover from first topic we have covered. So now we'll cover second option, the bearing capacity of main flotation from SPT data. So we can see here the net allowable bearing capacity based on SPT allowable settlement. So here is the allowable settlement. The net bearing capacity match constructed over the granular soil depends on the adequate determinant of the standard penetration resistance number. So N60 is nothing but N60 is just a SPT or a standard penetration number between bottom of the foundation and 2B. B is a beat of the below bottom, and B plus and this equation, and S equal to settlement. So you can see here S is a settlement, FD is given here which is less than 1.33. So this is the example we have seen here. The following are the result. This is the result of the standard penetration test of the field. Estimate the allowable bearing capacity of mat foundation 10 by 10 meter into 8 meter plan is given. Depth of footing is 10 meter and allowable settlement is 15 millimeter. So you can see here depth of first depth is 1.5 and 60 is 3 and the 3 when the depth is 3 meter, then L60 is 12, and when the depth is 4.5, then L60 SPD value is 11, and consequently when depth is 15 meter and found the L60 is 19. So we'll not consider the first SPT value or 160. Why? Because when we penetrate the SPT as a sample of spoon, when that in that time the soil will be disturbed. That's why we will not use first data is 9. So let's see. We can see here L60 is 12 11, so this is 12 11, so we will not use 9. So 12 11 7 13 11 14 17 16 19. So we are using from this data to from 19, so 12 to 19. So we will not use 9, because the sample when the sample is inserted into the soil, then soil will be disturbed. That's why we will not use the first data. And found N60 is 13. And FT we know 1.33, and DF is 3, and B is 8 is given, and found 1.12, which is less than 1.33. So now we'll use this equation N60 divided by 0.06. So N60 is found 13, we have seen here 13, and 0.06, and B here B plus 0.3 divided by NFD, and putting all this value, and found the ultimate net bearing capacity 392 kilonewton per meter square. So okay, now we will go to the compensated footing. So before we go into the compensating footing, we want to know what is the compensated footing. The compensated foundation is a specialized type of foundation where the weight of the soil excavated in the roughly equal to or greater than the weight of the structure being constructed, and this technique is reduce the net pressure of extracted of soil bearing soil below the foundation. So this is the main equation Q divided by DF, Q by A minus gamma prime DF. Okay, so this is the footing we have been seeing. The soil is excavated and from the footing. So compensated footing, the net pressure of soil is under the mat can be reduced by increase the depth, and the approach is generally referred to the compensated and sign deeper basement is okay. So you can see the compensated footing concept is coming from here. This is the mat foundation we can see here, and this is the EGL, and this is the this is the story of building. Compensated footing, we know the net average applied pressure is this is here. So for no increment, the net pressure of soil is mat foundation Q equal to 0. So that's why DF equal to Q by A. Okay, so compensated footing we can see here. Here is an example. Okay, so let's go to the an example of compensated footing. So a mat foundation of clay is dimension is given here, 15 into 10 with ABC equal to 16 kilometer meters, and saturated 18 kilometer per cubic meter, and total dead load and live load mat on 20 millinewton, and determine the depth of mat. Assume the fully compensate of foundation, and what will be the depth of mat of factor of safety is 3 against the bearing capacity of failure. So first of all, we can give the given the data is B A L C saturated and gamma prime is equal to it, and Q equal to 20 millionewton, and depth when we have to find out depth of footing when fully saturated and the partially saturated. Okay, so for question 1 we have to For no increase in net pressure on soil, mat foundation or Q level should be 0. That's why depth of footing Q divided by F and found 19.53, which is about to the 64 feet. So this is too much. So 9.53 meter or 64 feet depth of footing is mat foundation is too much. So we cannot provide this depth of footing for mat foundation. We have to reduce the depth of footing. So now we'll see how we'll reduce. So when phi equal to 0, then n60 nc and gamma nq we will found from Meyerhof bearing capacity. This is the bearing capacity table, and a shape factor and depth factor. We have at firstly we have taken the DFTs to we are assuming this, and use the Meyerhof equation and found this equation u equal to ultimately 5361. This is the equation. So now we'll use this equation q allowable divided by q factor. So q allowable is nothing but q divided by in gamma prime df, and putting this equation, found this equation. So now we'll use this equation here. So here this is the equation we are putting here, and we know the net equal to ultimate divided by q, and net is found here. This is the net value 393. So this value is putting here, and q equal to we have found here. So depth is footing 4.9 meter. One factor of safety is 3. So this could be a answer, but we will trial again. Now we'll put the depth is 4.9, the value of equation 1, and the recalculate the equation 1, 2, 3 after the gaps. And df at firstly we have taken the dft is 2. So now we'll get the dfa depth of footing 4.9. So we'll use here the 4.9 and recalculate all things, and found q ultimate. The equation is here. So again we will use q allowable equal to q net, which is we have found this equation, and ultimate equation is here, and found depth of footing 4.09 meter. So this is the answer. So this is the reasonable what I would say reasonable or reasonable answer. So this we can say this mathematics and this mathematics are all the same math. I have calculated here. So let's again we can see here. So for the we have found depth of df equal to q by I, which is 19.4. So for the math to be fully compensated, and factor of safety you can see here q and found here, and this is an equation. So we can see here another equation for ultimate bearing capacity is a Meyerhof equation, but we have to calculate the depth factor, shape factor, depth factor, and inclination factor. So we can when phi equal to 0, and found this value from the chart Meyerhof 5.011 and 0.00, and found shape factor also, and we have putting all these values here, and df equal to unknown. So df equal to 1 and found depth of footing 4.91, factor of safety is 3. So so let's see another example. So let's see another example. Here is another example. So determine the depth of footing fully compensated is given for mat foundation with the dimension of 14 meter into 8 meter for two different load applied, which is 12 milli mn and 20 mn Newton The mat is will be constructed on depth bed saturated clay with Cu 50 kilopascal and saturated gamma saturated 70.75 kN per cubic meter, and mention the about the factor of safety of the mat footing for both cases. So we have seen here all the data is given when phi equal to 0, then we have found this data when q equal to 12 mm, then depth of footing will be 13.5 millimeter, which is 44.3 feet. So 13.5 meter or 44.3 feet depth of footing of mat foundation is too much. So we cannot provide this depth of footing for mat foundation. We have to reduce the depth. So now we'll reduce the depth. How we'll reduce? At first we will use a shape factor and depth factor. So at the first trial we are using depth factor is 2, and when phi equal to 0, then nc and nq is taken from the Meyerhof chart, and found q equal to gamma prime df and df equal to unknown. Now we'll use the Meyerhof equation, and q ultimate will be this equation as the df equal to unknown, and allowable we can use gamma q by a into gamma prime df, and found this equation. So now we know allowable equal to q ultimate minus q equal to factor of safety. So ultimate is here, q allowable is here, and ultimate we have found the equation here, and this is the equation. So we are using we are taking this equation, and q equal to 7 gamma prime df, and found depth of footing 1.113 when which is very reasonable when factor set to 3. So let's see another trial. Footing 1.13, this is the depth of footing 1.13. Now we'll be putting depth of footing is 1.13, and found this factor, and q ultimate will be this equation, and q allowable will be this equation. So the allowable equal to ultimate q divided by factor of safety. So allowable is coming here, and the ultimate is taken here, and found depth of footing 1.36. At first we have found 1.13, and then 1.36, which is increasing. So now again we will try here, we will giving the trial when depth of footing taken 1.36, and ultimate will be like this, and putting this value here again, and found depth of footing 3.13. And again we will trial 3 when depth of footing is here, and ft is equal to like this, and ultimate will be this equation, and putting this equation, and found 1.32. So we can see the 1.31 and 1.32 is very close, so we'll use the 1.32 depth of footing. So for second purpose, we can we have for the second question we can see here the second question 20 mm. So now we solve the second question. So when the q equal to 20 mm, so we will use df equal to q into n, and found 22.5 meters. So it is too much depth, so we will have to reduce. So q ultimate we have used 7. This is the equation we have found. Now we can see here q allowable q by a into gamma prime df, and putting all this value here, and allowable value is coming here, q allowable equal to q ultimate divided by factor of safety. So q allowable is here, and ultimate this is the ultimate equation. So ultimate equation is here, coming from here, and q equal to we have used here 7.39 df, and found 10.3 meter, which is 34 feet. If you use df again here, then we have to calculate again and trial and error method. So today's lecture is ended. If you have any question, then let me know. I want to say again that the lecture is divided 3 types. One is bearing capacity of Raft foundation using Meyerhof equation, and second one Raft foundation, but it is the based on SPT or standard penetration data, and third one is compensated footing. So this is the today's lecture. If you have any question, then let me know. I will try to solve your question. Thank you everyone. Thank you.